Assalamualaikum and a very good day to everyone. Today, we will be presenting about our project which is related to applications of Faraday's and Lenz's law. Without any further ado, let's go with the content of our project. So the contents should involve electromagnetic induction, Faraday's law, Lenz's law, and magnet moving through a coil. Looking through electromagnetic induction, electromagnetic induction is the process by which a current can be induced to flow due to a changing magnetic field. Magnetic force, we look at the force experienced by moving charges in a magnetic field. The force on a current carrying wire due to the electrons which move within it when a magnetic field is present is a classic example. This process also works in reverse, either moving a wire through a magnetic field or equivalently changing the strength of magnetic field over time can cause a current to flow. Moving on with Faraday's law, this relates the rate of change of magnetic flux through a loop to the magnitude of electromotive force, which is epsilon, induced in the loop. The relationship is epsilon is equals to dV over dt. The electromotive force or EMF refers to the potential difference across the unloaded loop, for example, when the resistance in the circuit is high. In practice, it is often sufficient to think of EMF as voltage, since both voltage and EMF are measured using the same unit, which is in volt. Next, we go through to the Lenz's law. Lenz's law is a consequence of conservation of energy applied to the electromagnetic induction. While Faraday's law tells us the magnitude of EMF produced, Lenz's law, on the other hand, tells us the direction that current will flow. It states that the direction is always such that it will oppose the change in flux which produces it. This means that any magnetic field produced by an induced current will be in the opposite direction to the change in original field. Lenz's law is typically incorporated into Faraday's law with a minus sign, the inclusion of which allows the same coordinate system to be used for the both flux and EMF. The result is sometimes called as Faraday-Lenz law, which is epsilon equal to negative dV over dt. In practice, we often deal with magnetic induction in multiple coils of wire, each of which contribute the same EMF. For this reason, an additional term N representing the numbers of turns is often included, which is epsilon equal to negative N times with dV over dt. Lastly, we have induction from a magnet moving through a coil. So there is an Faraday experiment where a magnet is passed through a coil. As we can see here, magnet, when it is at rest in or near the coil, no voltage is observed. Secondly, magnet moving towards the coil and some voltage is measured, rising to a peak as the magnet nears the center of the coil. Magnet passes through the middle of the coil and measured voltage rapidly changes the sign. And lastly, magnet passes out and away from the coil, voltage measured in the opposite direction to the earlier case of the magnet moving into the coil.
This is Faraday's shaking torchlight. So After a few minutes of shaking it, flux occur and produce a current and store it in capacitor. Right? When the capacitor has charged, the light can be lit by pressing the switch like this. Yeah. Alright.